Yep. Okay, so welcome to our last session. So our first speaker will be Andrea Malchiodi, speak on the Sobolev quotient and CR geometry.
Thank you. Also, thanks to the organizers of the conference for inviting me here. So it's a real pleasure. So it was said many times that Alice and Paul like to talk to young people. So I was one of those lucky ones when I was a student. So they really devoted me a lot of time, and I'm really grateful to them. I'm sure they enjoy talking to young people, but there's that time of the year around the end of the fall when it's time for reference letters. So young people, okay, would talk to you, but then ask you reference letters all together. So I know they also helped me a lot on that side. So I'm also grateful for them for all the support to my work. All right, so I like to talk about some joint work with Zixing Cheng and with Paul. So let me start. Oops. Oh, thank you. With a classical problem. So in geometry, people always try to find like the best metric, best possible metric on a given manifold. Okay, say compact. All right. So one way is to try to deform the metric conformally. So dilate it pointwise by a positive factor lambda of x. In 2 dimensions, there is a classical problem, uniformization problem, which was solved more than a century ago. And that tells you that, so the problem is about trying to find the metrics with constant Gaussian curvature. So it would turn every 2-dimensional surface into a model space. In dimension greater or equal to 3, there is the well-known Yamabe problem. So Yamabe posed the same question, trying to uniformize the scalar curvature, and his motivation was trying to use that as a first step to try to attack Poincaré's conjecture. So that didn't really work out, but still the problem got a lot of attention. Okay, so this boils down to solving some PDE. You rewrite the conformal factor lambda in this convenient way. That gives you a clean formula for the change, conformal change of scalar curvature. So in particular, if you want to make the scalar curvature of the new metric constant, you need to solve for this equation. On the left-hand side, you have an operator which is called the conformal Laplacian. So it behaves nicely when you change conformally the metric. And on the right-hand side, you have u to the critical Sobolev power multiplied by r bar. So r bar is the constant, so that's the constant scalar curvature you want to attain. All right, so how do you attack this problem? You can view this constant r bar as a Lagrange multiplier. So you can try to find solutions looking for minima of this Sobolev-Yamabe quotient. Okay, so if, for example, you normalize, so this power makes this quotient homogeneous of degree 0. So it's invariant if you scale u by a constant. So you can think of, for example, normalizing the denominator, and then the other Lagrange equation for the numerator with the denominator constraint would be exactly this one. All right? All right, and then you define the Sobolev-Yamabe constant as the infimum of this quantity. So you hope to find a global minimum. If the minimum is attained, then you have a solution of your PDE. Namely, you get constant scalar curvature. Okay, so you could study the same problem in Rn. So you have the Sobolev-Gallardo-Nirenberg inequality. So the L2 star norm of U in Rn, where always in dimension greater or equal to 3, is bounded by the Dirichlet norm. Okay, and so as we did previously for a compact manifold, you can define this infimum also for functions in Rn. Minimizers have been classified independently by Oban and Talenti in '76. who proved that if you complete a space of functions which are compactly supported and say infinity, well, the minimizers are these special functions, so which I will call bubbles or Oban-Talenti functions. There are invariances here because the problem is critical. So of course you can translate any minimizer, but you can also dilate. So there is this scaling factor lambda, and the bigger is lambda, the more concentrated will be the, say, energy or the volume of this function. And since lambda can be arbitrary, there is no preferred piece for the scaling of these solutions. So they could be arbitrarily concentrated near a single point. So that's called by well-known lack of compactness in the Sobolev embedding. Okay. Okay, so since the sphere is known to be conformal to Rn via the stereographic projection, it turns out that when you compute this infimum in Rn, this is like computing the infimum of the Sobolev-Yamabe quotient, as I defined before, for the case of the compact manifold being equal to the sphere with a round metric. Okay, so you have this equivalence. All right, let me spend a word about the case of bounded domains. Okay, so you could try to consider the Sobolev quotient instead of in Rn in a finite domain. Okay, so try to reach the infimum for functions that are supported inside a bounded domain. Well, in this case, the infimum coincides with the infimum of Rn, but it is never attained. And the reason is exactly the lack of compactness of the embedding. Okay, so typically, minimizing sequences would tend to peak inside a point in omega. So there is also a study about, a more precise study about this this phenomenon. So you could for example, lower a little bit the exponent here. You would find the sequence of minimizers, and in the limit, as the exponent converges to the critical one, they behave exactly in this way. And people can also tell you where the blow up occurs. The point is that in Rn, you can always use dilations to recover compactness. Okay, so the problem is compact up to dilation, but that's not the case in a domain. Okay, so if you have a function supported in omega, you cannot enlarge it because it will escape this space. All right, so let me describe briefly the history on the Yamabe problem. So Yamabe tried to use actually the approach I just described, lower the exponent and try to pass to the limits. But there was a gap because he didn't quite consider this possible behavior. So the weak limit of a sequence of approximation solutions being 0. Okay, so he assumed convergence, but that might not be the case. So this was fixed partially by Trüdinger. So he proved that you can solve for the Yamabe problem provided the infimum of the Sobolev quotient is smaller than some dimensional constant. So some small epsilon n depending on the dimension. In particular, that's always possible when the infimum is 0 or negative. So those are the somehow easy cases of the problem. So the somehow sharp inequality was found by Oban. So he proved that whenever the infimum is strictly smaller than the spherical one, then you have compactness of minimizers. The reason is that somehow this Sn, so the infimum for the sphere, is the minimal energy threshold to have a blow up of solutions. So if you stay below, you don't have enough energy to blow up, and you must stay compact. Okay, so he also verified this inequality in large dimension when the manifold is not locally conformally flat. Okay, locally conformally flat means that locally you can find a conformal deformation of the metric, which is the flat metric. Okay, unless you are exactly on the sphere. And in 1994, Schoen proved that you have the strict inequality in all the remaining cases. Okay, so when you're not conformally equivalent to the sphere, when the dimension is less or equal to 6, or when the manifold is locally conformally flat, but not globally equivalent to the sphere. Okay, so for each case, and we have two complementary proofs, then you can always find the solution of the Yamabe problem by minimizing the Sobolev quotient. Okay, so let me try to describe this procedure. So how they can get this inequality and why the proofs works in these complementary cases, perfectly complementary cases. So that was quite amazing. Especially, why is there a difference in dimension? Okay, so the inequality is proved using Aubin's Talenti functions. So you can use them as competitors when trying to estimating the Sobolev-Yamabe quotient. Okay, so fix a point P on your compact manifold, and consider a highly peaked bubble function centered at the point. Okay, so since locally the geometry of any manifold is Euclidean, and since you're dealing with a highly concentrated function, then the quotient evaluated on this function will be close to the Euclidean one, which is equal to the spherical one. Okay, so you get very close to the Euclidean or spherical infimum. But then you're on manifold, so you hope that the geometry might give you corrections with a good sign. And that's actually what happens, okay? And why is there a difference in dimension? Well, these extremals have a decay rate at infinity of order 1 over x to the n minus 2. And you see the bigger is the dimension, the faster is the decay. So that's why somehow the effect of geometry is more localized in high dimensions. So this is what Aubin proved. Okay, so he proved that when the dimension is greater or equal to 6, the leading term in the geometric corrections is a local quantity. It's minus the Weil tensor squared divided by lambda to the 4. Okay, so lambda is this scaling parameter here, and it is large, so this correction is actually small, but it has a right sign. And so the Weil tensor is the tensor which picks up precisely, so it tells you whether the manifold is locally conformally flat or not. If it is not locally conformally flat, you can always find a point where the tensor is non-zero, so you can show that your infimum is strictly lower than the one of the sphere. Okay, while in low dimensions the correction is of global nature. Okay, the heuristics is that it has to do with the Green's function of the operator. Why? Okay, so consider a function which looks like one of these extremals, and you're dealing with a solution of the PDE of this type. So you have this operator, which I call LG on the left-hand side, the conformal Laplacian. So this solves for a right-hand side, which is highly concentrated. So if you expand it distributionally, you find a Dirac mass at the point P you chose, multiplied by 1 over lambda. Okay, so at a small scale, your say approximate solution would look like this one of these extremals, but away from the point P, it will look like the Green's function of this operator, the conformal Laplacian. So that's why the Green's function enters in the business. So as I said, at large scales, a solution looks like the Green's function, and the correction you pick up is given by the next order term in the Green's function expansion. So this operator has principal term equal to the Laplacian. So the Green's function has a principal term, the Euclidean Green's function. But then there is a next order term, which I call A, and the correction is minus A divided by lambda to the n minus 2. Okay? So first of all, you see that when n is equal to 6, there is a matching between these two corrections. So in low dimension, this is dominating. In high dimensions, this is dominating. And so not only you pick up this term, but okay, so to show that you go exactly strictly below the quotient of the sphere, you need to prove that A is positive. That's actually a very hard say problem because this term A is a global quantity of the manifold. Okay, so this first term in the global expansion of G is a totally universal term. okay? But the next order term depends on the whole geometry of the manifold. So it's pretty much like the Robin function for the Laplacian in a domain. It's a global object. So it's very hard to understand it. Okay, so to do it, so which was done by Shen and Yao, you need to actually go into general relativity, at least it's their approach. Okay, so I need to introduce asymptotically flat manifolds. So I stick to 3 dimensions. So asymptotically flat manifolds are unions of a set K, compact and possibly with topology, and a complement set, which is called usually an end, which is diffeomorphic to the 3-dimensional Euclidean space with the ball removed. Okay, so we're talking about objects of this type. And you also require that the metric converges to the Euclidean one at infinity at some rate, which I will not discuss. Okay, and these objects are interesting in general relativity because they describe isolated and static gravitational systems. So they are rolled, okay, let me discuss first some examples. Okay, so one example is the Schwarzschild metric, which describes a black hole of total mass m. So in polar coordinates, you have an explicit expression, and this is a metric for which at radius equal to the mass divided by 2, there is a minimal surface which represents physically the event horizon, so the no escape region. Another example, which is the one I'll be interested in, is that of a conformal blow-up. So you start from a compact manifold, say 3-dimensional, fix a point P, and then near the point P, you blow up conformally the metric by a factor which is proportional to the inverse of the distance to the 4. Okay? I will explain why this is a natural factor to put. Because, so if you invert coordinates via Kelvin inversion, so a sphere inversion, well, then a metric which behaves in this way, the x over x to the 4, in the inverted coordinates becomes asymptotically the Euclidean one. Okay? So by blowing up a compact metric at this rate, you're going to find, by inverting coordinates, exactly an asymptotically flat manifold, as I described before. Okay, so these gravitational systems are described by Einstein's equations, which are the following. So Rij is the Ricci tensor, Rg the scalar curvature, Gij the metric. And formally, this is the Euler-Lagrange equation of this functional, so the Einstein-Hilbert functional, which is nothing but the integral of the scalar curvature. So if you consider compactly supported variations of the metric, then you're going to get this Euler-Lagrange equation. But more precisely, so if you take a variation of the integral, so including scalar curvature and the volume, you're going to find actually the Einstein tensor plus some divergence term. So when your variation of the metric is compactly supported, after integration the divergence is gone. But in general, if you can consider variations of the metric which preserve the asymptotically flat structure, then you get some sort of flux at infinity. And there enters the mass, okay? So from this flux at infinity, you can define a quantity, which is the mass. I will show a formula later on. So that's when you take the derivative with respect to the metric of the action plus the mass, you get exactly the contraction of the Einstein tensor with the metric variation. And this mass can be computed as a boundary integral at infinity. So that's called the ADN mass. And so you integrate some expression on the derivatives of the metric over a large sphere, which is going out to infinity. So it's really like a flux term induced by the metric. Okay, so if you do that computation for the Schwarzschild metric, you get exactly the mass of the black hole, so which is nicely consistent. In the case of conformal blow-up, Okay, you can use the Green's function to blow up the metric at the rate I described before. Okay, so in this case, in 3 dimensions, the metric behaves asymptotically like the distance from the pole to the -1. And in this case, the mass coincides exactly with the next order term in the expansion of the Green's function. Okay, so I showed Schoen's expansion of the Sobolev-Yamabe quotient. If you could prove that this term A is positive, then you can minimize the Sobolev quotient. And proving the positivity of A corresponds exactly to proving the positivity of the mass. And this is a very deep theorem due to Schoen and Yau. So this was in dimension 3, dimension from 3 to 7, and then from last year in all dimensions. I'll just state the 3-dimensional theorem. So if the scalar curvature of an asymptotically flat is non-negative, then the mass is non-negative. With equality, if and only if the manifold is isometric to the 3-dimensional Euclidean space. Okay, so the proof of Schoen and Yau used the construction of stable asymptotically planar minimal surfaces. So they solved, arguing by contradiction and assuming the mass is negative. They used the solutions of Plateau's problem. So you prescribe as a boundary datum, boundary curve for a minimal disk, a large circle, which is going off to infinity. And they proved the existence of a limit for the solutions of the Plateau problem. And they would converge to a stable minimal surface. But then they used the second variation of the area with the condition that the scalar curvature is non-negative to show that this limit surface cannot be stable. So arguing by contradiction. And then came a proof by Witten in 81 using the Dirac equation, but requiring, of course, the spin structure of the manifold. And that's a rather short proof because the mass appeared as an integral using the Bochner-Lichnerowitz identity. So a quite simple proof and amazing to me. Okay, in a sense, both approaches are fundamental to study manifolds with positive scalar curvature, as done by Gromov, Lawson, or Stolz. So we heard some aspects of this yesterday. Okay, so the positive mass theorem, as I said, was used by Schoen to prove Yamabe's conjecture in some cases, but not only. So there is a relation to the Yamabe invariant, so which is vaguely the largest possible scalar curvature you can put on a given manifold, leading to some compactness or finite topology theorems with contributions also from Alice and Paul with Qing. It has been used to determine also like the center of mass of gravitational system, finding CMC foliations at infinity. If you consider 3-dimensional space, that's foliated by spheres, and you can center spheres wherever you want, but not on an asymptotically flat manifold. So if you want to find constant mean curvature spheres with sort of large radii, they need to be centered near the gravitational center of mass of the system. Okay, so you cannot put them wherever you want. And there is work in this direction by Huisken Yau, Qing and Tian, and Eichmeier-Metzger, especially when you want to understand, for example, isoperimetric sets with large and fixed volume. Okay, so the positivity of the mass is used crucially in this study. And finally, I want to mention also some relation to the stability properties of minimal surfaces, as done in recent works by Carlotto, Chodos, and Eichmeier. Okay, I'll describe now the case of CR manifolds. Okay, I recall briefly what are the ingredients involved. So for any point, I consider a 3-dimensional manifold, M3. So for any point, there is a contact structure, so a 2-dimensional plane psi, 2-dimensional distribution which is non-integrable. And so there is a CR structure, so a complex rotation J within this contact structure C. Okay, so J squared is equal to -1. And I call Z1 and Z1 bar the corresponding eigenvectors. So I assume that J of Z1 is equal to I Z1, and I denote by Z1 bar the conjugate of Z1. Okay, a contact form is a one form which is annihilating psi. And there is some, say, conformal structure there, because you can always scale such a one form to still have xi in the kernel. Okay, there is this assumption which is quite natural, pseudo-convexity. So you can use a theta wedge d theta as a volume form. Okay, so which has actually applications in the study of the D-bar-Neumann problem. So main examples, so there is somehow a flat model, the Heisenberg group, for which, say, the eigenvectors are the following one, and the operator J is the one sending Z1 into IZ1. And then there is the case, so that's also the expression of theta. And then the case of boundaries of complex domains. So if you consider the complex rotation J2 in C2, then the contact plane would be just the intersection of the subspace, which is invariant by J2, and the tangent space to the boundary. Okay. Okay, so Webster in 83 introduced, and independently also Tanaka, so introduced some differential geometric tools to study the biholomorphic problem. And in particular, he defined this Webster curvature, a scalar function which behaves conformally pretty much like the scalar curvature. Okay, so if you change conformally the contact form, as I said before, in this way, then the Webster curvature transforms nicely via this equation, which is totally similar to the transformation law of the scalar curvature. Okay, so here delta B is the sub-Laplacian, so you're just taking the vaguely the Laplacian just in the contact distribution. But since the distribution is non-integrable, this equation, being sub-elliptic, gains still some regularity properties. Okay, from the point of view of homogeneity, so this was noticed already in different talks, but somehow the missing direction, the non-contact direction, counts twice from the point of view of, for example, counting Hausdorff dimensions of sets, or like in Sobolev embeddings. Because the natural motion in these manifolds is always, say, tangent to the contact distribution. So if you want to reach points which are on the vertical, then you have to spiral around, which costs you length. Okay. And as before, so if you want to attack this problem and solving for constant Webster curvature, you can try to use exactly the same tools as before. So you can define a Sobolev-Webster quotient and try to uniformize exactly as we did before. Okay. In fact, this was done by Jefferson and Lee in dimension greater or equal to 5, proving somehow the counterparts of Tudinger and Aubin's result. This is a much more difficult problem because classifying the extremals in Heisenberg is much harder. So in Rn, you can use symmetrization, but here they have a really ingenious proof. I'll go back to that later on. Okay, so from now on, I will always suppose that the infimum of the Sobolev quotient is positive, otherwise it's an easy case. And I'll stick to 3 dimensions. So still in low dimension, you see the Green's function appearing, so of the operator appearing on the left-hand side before. Okay, so you can still expand the Green's function locally near a pole. And you're going to find that the main term behaves like in a standard way. So in this case, we're in dimension 3, but it's sort of similar to Euclidean dimension 4. The main term is the distance to the -2, so which would be like homogeneous dimension 4 - 2. But here rho, it was also mentioned by Paul today, is the homogeneous distance. So you see z and t scale differently. And then you have an next order term, which I still call a. So this is a global term. Okay, so blowing up again the contact form theta, as I did before using the Green's function, you obtain a manifold which is asymptotically like Heisenberg at infinity. You can define a mass, and that's actually proportional to this term A, so exactly as in the Riemannian case. Okay, however, there are differences in the CR case, okay? And one crucial difference is that is the embedability properties of abstract CR structures. So in high dimension, this was proved by Boutet and Monvel in dimension greater or equal to 5. So you can look at the book by Chen and Shaw for a reference. But it's not true in general for three-dimensional manifolds. In fact, say a random, a generic abstract three-dimensional CR structure is not embeddable. Okay. So this is a crucial dimension between the difference between dimension 3 or higher. Okay, let me introduce the Penitz operator. So the Penitz operator is a fourth order operator defined in this way. So each time I write a comma 1 or 1 bar, I'm using the covariant derivative with respect to z1 and z1 bar. And A here is the torsion, which I did not introduce. However, this characterizes the structure of CR functions. So as done in papers by Jack Lee, Case, Cianillo Yang, and Hirachi. Okay, this operator transforms nicely when you change conformally the contact form. So it's actually a pure pointwise covariant operator. And it enters crucially in the assumptions of this embedability theorem. So in 3 dimension, due to Cianillo, Chiu, and Paul. So if you have a complex CR manifold for which the Penitz operator is non-negative definite and for which the Webster curvature is positive, then it can be embedded into some complex space. All right, so we got then an integral formula for the mass, which is somehow inspired by Witten's proof of the positive mass theorem. So I will explain this technical assumption later, but okay, I consider a manifold which is asymptotically Heisenberg. So Heisenberg is described by coordinates z, t, and I assume that there is a complex function beta on n, which behaves like z bar at infinity. Okay, so then the mass has this expression, so you can obtain it via some tricky integration by parts formula. In a totally similar way, yes. I didn't write down the expression because I wanted to limit, say, the formulas, but the derivation is exactly the same. And it coincides with the next order term and the expansion of the Green's function if you do a conformal blow-up. Okay, but it's totally identical. Okay, so you get this expression, maybe not so nice, but say if this term is positive, if Webster is positive, this term is also positive. If Penitz is positive, this term is also positive. The only tricky term is the following one. Okay, so you get, say, 3 positive terms and 1 negative term. Okay, so the proof uses a tricky integration by parts. I mean, it's not so hard after you know what to do. Somehow the main idea was to bring in this Penitz operator, because this is a formula you can rewrite down in rewrite in like 1,000 ways, but so this was somehow the most conformally covariant way we found. Okay, so the idea was to bring in the Penitz operator, and the only obstruction to the positivity is the first term. But luckily for us, so there is a theorem by Shao and Jung who proved that I'm really grateful to them for for this theorem. So you prove that if you can find, say, an approximate solution, so you want to kill this term, so you want to solve for z1 bar of beta equal to 0. If you can find a solution behaving like z bar at infinity for which this quantity decays sufficiently fast, then you can actually make it vanish. Okay, but it was already quite a pain to find a right approximate solution. So that allows you to work in weighted spaces where they actually solve for this equation. All right, so out of this formula we got this theorem. So conformal blow-ups of compact three-dimensional CR manifolds. Okay, so suppose the Webster class is positive, so that the infimum of the Yamabe quotient is positive, and that the CR Penance operator is non-negative. Okay, so that's fundamental for us. Okay, so consider a point P at which you do the blow-up of compact form. Then the mass of the blown-up manifold is non-negative. And if it is 0, then you have to be congruent to the Heisenberg group or to the round to the standard sphere. Okay, so again, as I said, the CR mass is proportional to the next order term appearing in the expansion of the Green's function, and that allows us to find solutions of the Yamabe quotient, which are global minimizers of the solutions of the CR Yamabe problem that are global minimizers of the Sobolev quotients. And actually, previously, existence of solutions were known by work by Gamara and co-authors using some very involved min-max methods, so producing solutions not of minimal type, so usually typically they would have a very large Morse index. And there is also a flow approach by Chang and Ho. Okay, positivity is proved in higher dimension for locally spherical manifolds in a paper by Chang, Chu, and Yang. And I think later Chu will tell us, I don't see him. Yeah, there. The 5-dimensional case, I think. Okay, so the main difference between, say, the Riemannian positive mass theorem, which has no assumption other than the positivity of R, and our theorem is the positivity of the Penance operator. Okay, so you may wonder whether this is technical or not. Okay, well, I would like to point out that it is not a technical assumption. Okay, so consider the standard sphere in C2. And as I said, a random perturbation of the standard CR structure is non-embeddable, as proved by Burns and Epstein. Okay, so in these cases, the Penance operator cannot be positive definite by the theorem by Chanlilo, Chu, and Yang we saw before, because if Penance is positive, then the structure is embeddable. Okay, so random perturbations are not embeddable, so Penance cannot be positive definite. Okay, so we have this theorem. So in fact, you can find perturbations of the three-dimensional standard three-dimensional sphere arbitrarily close to the standard sphere, for which the Webster curvature is positive, of course, because you started with something with positive Webster curvature, but with negative CR mass. Okay, so somehow the positivity of the Penance operator enters crucially in this business. And one interesting case are Rossi spheres, so introduced by Hugo Rossi in 1965. So somehow you have a standard J0 on S3. So you sort of perturb, so you consider a slightly distorted structure depending on one parameter S. And when S is 0, you are on the standard sphere. And a nice property of these Rossi spheres is that they are homogeneous three-dimensional manifolds. Okay, so you have a one-parameter family of Rossi spheres, including the standard sphere. And we looked at the Sobolev quotient of Rossi spheres. Okay, so this is still work in progress. So for small, so not only there are cases in which the mass can be negative, but so the mass is used, the positivity of the mass is proved to show that the minimum of the Sobolev-Webster quotient is attained when the positivity of the mass fails, then you can also push somehow this relation. And we have this result. So for S non-zero small, the infimum of the Sobolev quotient on Rossi spheres is not attained. So you always know that it is less or equal than the one of S3. So in this case, it is equal but not attained. Okay, 2 words about the proof. Okay, so suppose you want to look for minimizers or almost minimizers. Okay, so we are on a structure which is close to the standard one. So you must be an almost minimizer for the standard sphere. But almost minimizers were classified by Jason and Lee in 88. So there are, it's more complicated, it's very complicated, but they have an explicit formula, so they can classify explicitly minimizers for the CR Sobolev quotient on the standard S3. So if you have a minimizer for the Rossi spheres, for S small, well, then you must be somehow Sobolev close to one of these. All right, but then you can expand literally with a Taylor series the Sobolev quotient on these Jefferson-Lee extremals. So when you are on the standard sphere, say Riemannian, the graph would be totally flat because it's a family of minimizers. Okay, and if you perturb the metric in the Riemannian case, then the Sobolev quotient goes below. Okay, because the infimum of the Sobolev quotient of a manifold which is not a sphere, Riemannian, is strictly lower than that. Okay, so a general perturbation in the Riemannian case bends the graph down. In this case, you can show that the graph is bent upward. Okay, so there is an effect which is totally opposite to the Riemannian case. But this works if you can have lambda, so the scaling parameter, in a fixed compact set of 0 infinity. Okay, so if you stay compact in, say, the Möbius group, then the Sobolev-Westberg quotient is higher than the spherical one. So then you will need to analyze somehow the tails of this graph. Okay, so when lambda is either small or large. Here the homogeneity of Rossi sphere helps because you can just stick to a single point. Okay, still you can do blow-up analysis. So suppose that you blow up, you say evade compact sets in the Möbius group, then you must blow up at a point, and you know that if you blow up at a point, the profile must be the Green's function of the CR Laplacian, conformal Laplacian. Okay, so we analyzed actually the mass of Rossi spheres to find that for S non-zero, the mass is actually negative, and you have an asymptotics for S small. Okay, so you have a negative mass which behaves quadratically in S. So it is 0, of course, when S is equal to 0, because you are in the standard sphere, but it's not positive, it is negative with a rate. And once you have that, well, then you can use a Kasdan-Warner identity to show that somehow this expansion for the Sobolev quotient keeps going also when you evade the compact sets in the Möbius group. Okay, so somehow it's not energetically, I mean, you're not critical if you, I mean, you are higher if you stay in a compact region of the Möbius group, but if you evade compact regions, you're not critical. So that's the idea. So the only critical point should be actually when lambda is equal to 1, corresponding to a constant conformal factor. So somehow there are, I would say, 2 surprising facts here. First of all, the relation between the attainment of the Sobolev quotient, which is basically an analysis PD problem, a bit geometric, with the property of amenability of the manifold, so which has to do with the complex analysis. The other thing is that we're dealing with a closed manifold. Okay, in the Riemannian case, you always have minima, but somehow the Sobolev quotient is more similar to that of a domain in a Rn. Okay, because when you try to minimize, minimizers would actually blow up at a point. I just conclude with some brief list of open problems. Okay. So Paul mentioned the relation to the Yamabe problem to this high-order invariance of surfaces, but we studied minimal surfaces in the setting, and it would be nice to see a role also of these. Another problem which has been recently settled is the compactness of solutions to the Yamabe equation with a quite surprising outcome. So you're compact if and only if the dimension is less or equal to 24, so as proved by Curie, Marquez, and Schoen, but you're not compact in high dimension. So for the CR case, actually the problem is entirely open because, as I said, one reason is that profiles of the Yamabe equation on Heisenberg have not been classified. So it was done by Jack and Jerrison for, say, finite volume solutions, but for general positive solutions, it is not known. There is also a study about, say, the subcritical equation here, but there are only partial results, for example, by Birindelli, Capuzzo-Dolcetta, and Coutry. One of the main reasons for which you cannot classify is that moving plane techniques are forbidden in this setting. Then there are also quantitative versions of the positive mass theorem. So the Penrose inequality gives you a lower bound on the mass depending on the total areas of outward minimal surfaces. So I draw just a simple picture here. And okay, you may wonder whether there might be an analog in this case. So the inequality was proved by Huisken, Ilmanen, and Bray using some geometric flows, in particular inverse mean curvature flow, but there is no result of this kind in the CR setting. And eventually, okay, you would like to understand whether there is possibly, we had only one example, but you would like to understand whether there might be a deeper relation between, say, the positivity of the mass and the attainment of the Sobolev quotient. So I stop here, and again, so happy birthday to Alice and Paul.
Questions?
So you showed that the Panite's assumption can't be eliminated. What about the scalar curvature assumption? Is it possible that that's somehow implied by the positivity of the Panite's operator?
That's a good question. I haven't thought about it. I would say, I mean, my guess is no. The positivity of Panite seems to be quite tied to the embeddability property. So if you have structures that are close to spheres, then it's almost an if and only if condition for the embeddability. But I didn't think of this relation to the scalar curvature. Okay, then no. Okay. Thank you.
Any other questions?
So for this rosy sphere, the Panite's operator is not positive then.
Exactly.
So is this positivity not a stable solution on standard S3 then, and on this Heisenberg space S3?
Sorry.
So that shows this positivity is not a Panite's operator, not a stable condition. What does that say? You perturb it, it's no longer positive. What happens?
Oh, so for the sphere,
Yes.
yeah, there is always a big kernel, which are the functions.
Yeah.
So that's an infinite dimensional space, and so their work is about understanding the deformation of this infinite dimensional space when you vary the CR structure. So when you take domains, for example, and so in that case you will get very small eigenvalues that are negative. Most of the work is about understanding the kernel, so somehow the variation of the kernel. So when you want to understand somehow the smoothness or the behavior of eigenvalues with finite multiplicity, that's kind of standard. So there are formulas by Kato, for example. So these things have been used to study atomic spectra. So somehow these kind of almost degenerate energy levels. So people in quantum mechanics worked a lot on these things. But there are always eigenvalues with finite multiplicity. So in this case, it's an infinite dimensional space, so it's much more tricky. Yeah, you want to show that somehow when you vary the structure, this infinite dimensional subspace doesn't vary like crazy.
More questions?